In this video, I want to cover the topic of unit vectors. A unit vector is a vector with magnitude of 1, and we use unit vectors as a standard for representing the most common directions in geometric space. This helps keep notation simple and consistent. In one-dimensional geometry, the only unit vector we deal with is I, which has a default direction generally of to the right, but technically you could use a vertical axis when you're doing one-dimensional mathematics. So then in that case, I hat would have an up as its default direction, but it totally depends on your frame of reference. Here we have horizontal frames of reference such that our axes are horizontal. And so I'm going to say that the default direction for the unit vector I is to the right, and then also technically you could have negative I, which would be to the left. I need you to understand that the reason why unit vectors are useful is because of the concept of a scalar multiple. So multiplying a scalar by a unit vector results in a vector with the same magnitude as the scalar, but now also with the direction of the unit vector. Let's graph the result vector of the scalar multiplication 3 and I hat, or in other words, the vector 3I hat. I'm going to create a vector here that is 3 units long and to the direction of the I hat vector. Of course, it's already drawn for you here, but that's an example of your 3I hat vector. Moving straight on to two-dimensional unit vectors. Now, each individual unit vector is always just assigned to one dimension. So if you have a two-dimensional frame of reference such that we have here, you're going to need two unit vectors. We're going to hold on to that I unit vector. That's going to represent the horizontal dimension, the horizontal axis. And then we're going to add in a new unit vector, which we're going to call J. So when working with two-dimensional vectors, we use I for horizontal and J for vertical. So the two-dimensional vector A, modeled below, has the horizontal component 2I hat and the vertical component 4J hat. And the reason why I know that is because essentially think about it like this. If I was to shine a light directly down onto vector A, then it would cast a shadow exactly 2 units long on the x-axis. So that's how I know its horizontal component is 2I hat. If I were to shine a light directly horizontally onto my vector A, it would cast a shadow that is 4 units long onto the y-axis. So I can say it has a vertical component 4J hat. And if you remember at all how to do vector addition, then adding the two vectors 2I hat and 4J hat would result, just as I've modeled here, in the resultant vector being my original vector A. And that said, you can get used to, and other mathematicians will understand, if you express vector A in terms of its components. In other words, any vector could be written, or specifically any two-dimensional vector can be written in the form AI hat plus BJ hat, where A is the magnitude of the horizontal component and B is the magnitude of the vertical component. That said, all you would need to do then to find the actual magnitude or length of the vector is to use Pythagorean's theorem, because all we're doing is we're creating a right triangle here with our given vector. So Pythagorean's theorem, in this case 2 squared plus 4 squared, would give us the magnitude of our vector A. So what's 2 squared? It's 4. What's 4 squared? It's 16. So the square root of 20 would be the length of vector A. Easy as that. In this example, we're going to start off with an empty two-dimensional grid, and the question is saying what's the sum of negative I hat plus 6J hat and negative 7I hat plus 7J hat. So what I'm going to go ahead and do is I'm going to go ahead and model each of these vectors on my two-dimensional grid, and I'm going to model each of them with their initial point at the origin. So for the negative I plus 6J is I'm just going to basically go 1 to the left and up 6. So that's going to look like 1, 2, 3, 4, 5, 6 right here. So I have a vector right there, negative I hat plus 6J hat, and I'm going to connect my vector to the origin, and I'm going to make sure I have a little arrow there. This is that first vector. Now in a different color, let's do orange. I'm going to model negative 7I hat plus 2J hat. That's going to essentially be me going 7 units to the left and 2 units up from there. So what that's going to look like is, let me just count to be sure, 1, 2, 3, 4, 5, 6, 7, and then up 2. Looks like I'm going to connect that to the origin, and I have modeled my two vectors. Now, I want to find the sum of these two vectors. There's two ways to do it. I could And I only even modeled them on the two-dimensional grid because we had a two-dimensional grid just here. And so what I could do really is I could take that first vector, negative I plus 6j, and I can add the second vector to it, tip to tail method. All right, tip to tail method is going to essentially create for me, it's going to create for me a third resultant vector, which I'm modeling here in blue. All right, and that's looking like it's going to be negative 8 I hat, because I'm 8 units away from the origin on the x-axis, and then positive 8, and then positive 8 j hat, because I'm 8 units up. I'm 8 units up from the origin on the y-axis. Now, that's just solving it graphically, doing tip-to-tail method with my vectors, but I can also just go ahead and take my negative I hat plus 6j hat, all right, and just directly add my negative 7 I hat plus 2j hat to it in this manner, just component to component. Negative 1 plus negative 7 is negative 8, all right, and then 6 plus 2 is positive 8. And then so that's my horizontal component, and that's my vertical component, and it's as easy as that. One more example I want to run with you is that given vector KL, which is written in its component form 8I hat minus 14j hat, write the vector that is parallel to KL but faces in the opposite direction and has a magnitude 2.5 times that of KL. All right, so essentially we're going to do two things here, and there's no need to really model this on a grid. What we're going to do here is algebra, because the first step that it wants us to do, which is make a vector that faces in the opposite direction, is easily achievable by taking KL, vector KL, which is 8I hat minus 14j hat, and multiplying both sides of it by negative 1. Now, if I multiply the vector KL by negative 1, of course I have the vector negative KL, suggesting that it's opposite. And that's going to be equal to negative, and I'm just distributing this negative 1 to each term, negative 8I hat plus 14j hat. Fantastic. But we're not done, because we also want our vector to be 2.5 times the magnitude of vector KL. So just like multiplying everything by negative 1 gives me the opposite, multiplying everything by 2.5 will give me a vector 2.5 times that of KL. So now I'm going to take this negative KL, and I'm going to multiply it by 2.5. And that means I'm going to take everything on the right side of my equation and multiply that by 2.5. And again, I'm going to distribute this factor into each term. So I'm going to be left on the left side with a new vector that is negative 2.5 times that of KL. And on the right side, I have negative 8 times 2.5. So let's see, 8 times 2 is 16. 8 times 2.5 would then be 20. So negative 20 I hat plus, let's see, 14 times 2 is 28. So another 7 on top of that is 35. 35j hat. The vector negative 20I hat plus 35j hat is both 2.5 times longer than the vector 8I hat minus 14j hat, and it's facing in the opposite direction. Thank you. I'll see you in the next one.